Welcome back. In our previous classes, we were actually discussing about the differentiability and derivatives of vector functions. We have defined the derivative, we have defined the differentiability, and we have seen a criteria to determine whether a function is differentiable or not in terms of its partial derivatives. And later we have tried to approximate a function with a linear, like a linear expression, and we have even encountered about the error. Right. So as our next session, we are going to define and explain the total differential of a function. Total differential. So we have been defining and using partial derivatives so far. And using these predefined partial derivatives, let's have a try to define and explain the total differential of a function. So consider a function f which is differentiable in a region, say in a region containing a point x0, y0. So consider a rectangle around x0, y0. Right. If this is the case, if I move slightly in x direction, say dx, and slightly in the y direction, say dy, I'll reach at a new point which will be obviously x0 plus dx, y0 plus dy, as I have made increments of dx and dy in x and y respectively. Consider this situation, and we have seen delta f, the change in f when we make such a change in x0, y0 to x0 plus delta x, y0 plus delta y, and we have explained this change in terms of partial derivatives. So we here define another concept, the total derivative, as df, which is equal to fx at x0, y0 into dx plus fy at x0, y0 into dy. So this is the total differential. Right. So you can think, how does this differ from our expression of delta f? Right. Or delta y. What was the expression we used for? Whatever. So df is equal to fx at x0, y0 dx plus fy at x0, y0 dy. Right. In fact, this expression of df, the total derivative, is capable of giving a better approximation for the change of f with respect to a change in x0, x and y. Or if you have a function f of xy, the measure df gives us a better approximation for the change of f when we make a change in x or y. Right, don't get confused, we'll move to an example which will make things clear. Right, now you may consider a situation. I'll give you a problem. We have a manufacturing unit of storage tanks. Suppose the unit manufactures storage tanks of cylindrical shape. Cylindrical shape. Assume this to be a perfect cylinder for now. So the radius of the cylinder is 5 feet and the height of the tank is, say, 25 feet. Right. So a manufacturing company manufactures storage tanks of cylindrical shape with these measurements, with radius 5 feet and height 25 feet. Determine how sensitive is the volume, with respect to its small change in radius and height. Make the question a little more clear. Determine how sensitive is the volume to a small change in radius and height. Right. As a first step, let's try to write down the volume as a function of radius and height. Say radius be determined or denoted by the letter r, height to be denoted by the letter h as a part of convention. So the volume of the cylinder or the cylindrical storage tank volume can be explained or expressed as a function of radius and height as pi r square h. You might be familiar with this equation. This gives the volume of a cylindrical cylindrical storage tank. So now we need to find the sensitivity of volume with respect to a change in R or H. What does the word sensitivity means? How far the volume V changes as we make a small change in R or H. Okay, see, what if we make a change in R, the volume will obviously change. Similarly, if we make a change in H, the volume will change. Are those changes the same? That's the question. Or how is it sensitive to the changes in R and H? Alright, so let's try to find df. df was actually giving us an approximation for the change of f. So not f here, it's dv here. dv. So what is dv here? Vr into dr plus Vh into dh. So what is Vr? The partial derivative of volume with respect to R. Pi and h will remain as constant. R square will be left and the derivative of R square with respect to R is 2R, so it will be 2 pi hr into dr plus what is Vh? H remains as h, so pi and R square will be constants, pi R square, and see derivative of h with respect to h is 1 into dh. So for now I'll just erase this part. So we got dv is equal to 2 pi rh dr plus pi r square dh. We have given the radius of our cylindrical tank to be 5 feet and height to be 25 feet. Right. So let's substitute these values in our equation for dv, which will give 2 pi into r, so there will be 10 into what is height, 25. So 250 pi dr plus pi into r square, so 25 pi dh. Okay. So what are this dr and dh here? Dr is actually a change in R and dh actually gives a change in h. So if you make a small change in R, say a change of 1. If we make a change of 1 in R, means change of R is 1, so dr is 1, and say change in h is also again 1, dh is 1. This means you are just giving an increment or decrement of value 1 or 1 feet in this case in the radius and 1 unit, 1 feet in this case for height. Okay, so dr and dh to be 1, then dv will be 250 pi plus 25 pi, which is 275 pi. Right. This happens when we make a change of 1 unit in both radius and height. If you make a change of 1 unit in both radius and height, the volume will change by 275 pi units. Right. What if we change only 1? We don't change height here, we just change radius. This will remain as it is, and 25 pi into dh, change in height. We haven't made any change to height now, so it will be 0. So it will be 250 pi. So if you make a change of 1 unit in our radius, the volume will change by 250 pi units. Similarly, what happens if you make a change in height, not in R? R remains the same, and you make a change of 1 unit in height. So the equation for dv becomes 250 pi into what is dr then? Dr is 0 since we haven't made any change in the radius, plus 25 pi into dH is 1, so it will be 25 pi, right? So if you make a change of 1 unit in height without making any change in R, the volume will change by 25 pi. So this actually shows that volume is actually a little more dependent over radius. Or in other words, if you make a small change in radius, it can drastically change the volume than the same change in height. Right. So this actually gives the sensitivity of volume with respect to radius and height. So far we were discussing about changes of function with respect to change in the variable, or how does the function change when we change the inputs. Right. There are three measures which we actually need to re-emphasize. They are the absolute change, relative change, and percentage change. So what is absolute change? You need to remember these names as well as the formula. The actual value of absolute change is delta f. Consider we have a function f of xy. See, this is our underlying assumption. F of xy is a function of x and y, and based on that function we try to explicitly give some formula. So dou f is the actual value of absolute change, and now we have seen a better approximation for delta f as df. Right. The next is relative change. Relative change. Relative change can be the actual value of relative change is delta f by f at x naught y naught. Right. This is the formula for relative change of f at x naught y naught. This can be better approximated by df by f of x naught y naught. Now we have percentage error. As you can just imagine, this is nothing but the percentage of percentage change, not error, the percentage of this. So it will be delta f by f of x naught y naught into 100, and can be approximated as df by f of x naught y naught into 100. So relative change multiplied with 100 will give you the percentage change. Right. See, don't get confused with these things. It will be much more clear when we move to an example. So don't waste time and let's move on. So let's go to an example of this. Estimate the absolute change, relative change, and percentage change of the function f of xy equal to pi x square y when the variables xy changes from 1 5 to, say, xy changes from 1 5 by amounts dx equal to 0.03 and dy equal to negative 0.1. Right. So we need to find the relative change. So we need to find the absolute change, relative change, and percentage change of the function f of xy equal to pi x square y when xy changes from 1 to 1 5 with amounts dx 0.03, dy equal to negative 0.01. So actually we move 0.03 points in the x direction from 1 5 and 0.1 units in the negative y direction from 1 5. Right. See, have you seen this function before? This is the function we have just used to evaluate the volume. We used r and h instead of x and y. It's the same, the volume function. So let's try to approximate the the absolute error, which was df. So what was df? fx into dx plus fy into dy. Remember, I just write fx and fy, but you should keep in mind that fx is evaluated at x0, y0, which is 1, 5 in this case. Similarly, fy is also evaluated at x0, y0, which is 1, 5. Right. So what is fx here? Fx equal to 2 pi x y. Fy is equal to pi x square. Right. What is dx? Dx is given as 0.03, dy is given as negative 0.1. So let's plug in these values into our equation. So fx evaluated at 1, 5. So x equal to 1 and y equal to 5. So 2 into pi into 1 into 5, which will be 10 pi into dx is 0.03 plus fy is pi x square. X is pi x square, x is 1, so it will be a pi into dy is negative 0.1. So simplifying, this will give 10 into 0.03 is 0.3 pi minus 0.1 pi, which is 0.2 pi. Right. So we got the value of absolute change. Now let's find the value of relative change. So what was the formula for relative change? The approximation formula df by f at x naught y naught. f of xy was pi x square y. Right. At 1, 5, which was our x naught y naught in this case, f will take the value f of 1, 5 is equal to pi into 1 square into 5, which will be 5 pi. Right. So now we have the value of df here and f of x naught y naught, which can be used to find the relative change. df is 0.2 pi and f of x naught y naught is 5 pi. So the relative change is 0.2 by 5. If you want to, you can further simplify this. Right. So on further simplification, this will be 0.04. Right. So what is the percentage error then? Percentage error can be found as found by multiplying the relative change df by f of x naught y naught by 100, which is 0.04 into 100, which is equal to 4%. Okay, so what does this mean? So what was the absolute change here? Was 0.02 pi. So 0.02 pi was actually the real change or the approximation to the real change when we make a change of 0.03 units in x and negative 0.1 units in y from 1, 5. Okay, and we got the relative change to be 0.04. This actually measures the relative change, right? So what does relative change means? The change with respect to or the change in relation to the actual value. The change in relation to the actual value. As a ratio, we express it as a ratio and we got to simplify it. Now, what is percentage change? What percentage of the actual value is being recorded as a change? What percentage of the actual value is being recorded as a change? Or simply, what percentage of the actual value is the change? Right. So this is about absolute change, relative change and percentage change. Okay, now let's hit another example of the same concept. Suppose the volume of a cylinder is measured using the formula V equal to pi r square h. To use this formula, we practically measure radius r and the height h using a scale or a ruler, right? So during the measurement there is an error intruded in both r and h. It is given that the maximum error in measuring the radius is less than or equal to, so I call it ER, the error in R is less than or equal to 2%. Also it's given that the maximum possible error or the maximum error intruded in measuring the height is something less than or is equal to 0.5%. So the maximum error possible in the measurement of R is 2% and the maximum error occurred in the measurement of height is 0.5%. So these are actually the percentage errors, or in the terminology we have used before, these are the percentage changes. Okay, so the question is calculate the percentage error or percentage change in calculating the volume V using this formula. Right, so what do we have now? We have the formula for volume, we have the maximum error intruded in radius and the maximum error intruded in height. Alright, let's try to find the maximum or the percentage error in calculating V, or the percentage change in calculating V. So the percentage change is given as dou V by, or it can be approximated as dV by V into 100, right? So what is dV then? Let's try to find dV first. dV, we have seen this equation several times now, so it's just a matter of time to write the dV. So it is 2 pi RH dr plus pi r square dh. Vr dr plus Vh dh, right? So what is dV by V? The whole expression divided by V. V is nothing but pi r square h. So 2 pi RH dr plus pi r square h, pi r square dh whole divided by pi r square h. Can we cancel out something? Some non-zero constants? Yeah, we have pi which can be cancelled out. So let me clear this off. So dV by V will be now so pi and pi can be cancelled, r square and an r can be cancelled out here. What will be left? 2h by h can also be cancelled out, so it will be 2 by r, right? 2 by r plus, here pi will be cancelled out, r square will be cancelled out, so dh by dr will be here, dh by h, right? So dV by V is now 2 by r dr plus dh by h. So what is the percentage error or percentage change? dV by V into 100, which is equal to 2 by r into dr into 100 plus dh by h into 100, right? See, we just multiplied the whole expression with 100. See, let me be there. We have given the information that the percentage error in R is less than or equal to 2%, which means the percentage error in R can be expressed as dr by R, right? So this is the change in R and this is the actual value of R, dr by r into 100. So this is how we express percentage change. Similarly, EH is less than or equal to 0.5% means dh by h is dh by h into 100 is, see, the error of radius, the error in measuring radius is less than or equal to 2% means dr by r into 100 is less than or equal to 2. Similarly, dh by h into 100 is less than or equal to 0.5. Now can you find a dr by r here? Similarly a dh by h here. So we can try to replace these values with this. So we don't have much space on the board, so let me clear this down. So dv by v into 100. We are replacing something with a greater quantity or a bigger quantity, so we'll have a less than or equal to sign. Or to be a little more precise, we don't know whether this volume increase or decrease, right? We are just estimating the change. So we just consider the absolute value dv by v into 100. See, if this is negative, we consider that to be decreasing, or if this is positive, we consider that to be increasing. We are not interested in calculating whether it's increasing or decreasing for this case. So we consider the absolute value. So absolute value of dv by v into 100 will be this. Will be less than or equal to, using the triangular inequality, we will have 2 dr by r. So 2 can be taken outside being a positive quantity. So 2 into absolute value of dr by r into 100 plus absolute value of dh by h into 100, right, which will be less than or equal to, we can replace this dr by r into 100 with 2, since the maximum percentage error of radius is 2%, plus dh by h into 100, it's actually given as 0.5, which is the maximum possible error intruded in the measurement of height. So what is this? 4 plus 0.5, which is 4.5%. So the maximum error which can be intruded in calculating the volume using the formula given as v equal to pi r square h is 4.5%. Right. So this is another application of using the percentage error. Here we got the error limits for the variables or the inputs, and we try to analyze the error limit for the dependent variable v. Right. So the story of percentage changes come to an end here. I request you to find certain examples from your textbooks and try to solve them down to get familiar with these concepts. Right. It's actually important both in your exam point of view and for your higher studies, obviously. So now we have been discussing all these concepts for functions of two variables. Is it any way limited to functions of two variables? Or is there any necessity that all these concepts to be limited for functions of two variables? No way. We can extend all these to functions of any number of variables. Right. So what happens if you have a function of more than two variables? Let's try to find what's happening inside for certain concepts which we have been discussing so far. We have seen the linearization of a function. I think you remember the formula, like fx into dx or fx at x naught y naught into x minus x naught plus fy at x naught y naught into y minus y naught. So what happens if we have a function of three variables? Say f of x, y, z. Suppose we have a function of three variables. How does the linearization of this function look like? Say L of x, y, z. See, we can directly extend the formula for two variable functions as fx at say x naught, y naught, z naught. Suppose we are calculating the linearization at x naught, y naught, z naught into x minus x naught plus fy at x naught, y naught, z naught into y minus y naught plus f z of x naught, y naught, z naught into z minus z naught. Right. So in the same fashion, we can extend the definition and expression for linearization to any number of variables. So what happens if we have another variable? There will be another term included here. Right. That's perfect. So what about total differential then? How did we define the total differential for two variable functions? we define it to be, or further, before that, we have seen an error estimate for linearization in two variables. So how does the error estimate for more than two variable function look like? Error in the linearization. We have seen this as e of x, y, z, x, y. Now we extend the same definition to three variables. So for a three variable function, e of x, y, z will have the absolute value less than or equal to 1 by 2 into m. See, let me write it in the next line so that's a little more lengthy than the previous one. So 1 by 2 m into x minus x naught plus y minus y naught plus absolute value of z minus z naught whole square. In our previous case of two variable functions, what was f? The maximum of mod fxx, fyy. Right. So here m is not limited to two functions or two derivatives. So m is actually now upper bound for mod fxx, mod fyy, mod fzz, mod fxy, mod fyz, mod fxz. Right. So now m has to be the upper bound for all of these absolute values. So things change accordingly. The change reflects everywhere. But still we can directly extend the formula for any number of variables. Right. Perfect. So let's move to total differential. How does the total differential of a function of three variables, say f of x, y, z at x naught, y naught, z naught look like? We follow the same fashion. Let's extend the formula. So df at x naught, y naught, z naught is equal to fx at x naught, y naught. I'm not going to write that again. Fx into dx plus fy into dy. This was actually the expression for two variables. So here we have another variable, so another term will include. So fz into dz. Actually these fx, fy and fz are actually evaluated at x naught, y naught, z naught. I haven't written it explicitly, but remember that.